Hi folks! Welcome back to the Nibbles and Bytes Studio Workshop. At this point in the series, we've covered the basics of most of the components of the 128, which gives us input, video, and processing functionality. Now the second to last piece of the puzzle for making a video game is sound, so we'll cover the SID chip next. The SID chip is a bit of an odd duck. It's primarily an analog device and uses analog modulation and filters to produce sounds, while it still provides a digital interface to the CPU. It also provides an interface for reading the analog values of the paddles, and provides digital outputs for reading random numbers. For this episode, though, we're going to focus on the sound aspects of the SID chip. So without further ado, let's head to the whiteboard. Speakers create sound waves in the air by vibrating back and forth. But when we graph this over time, it looks like a wave like this. The SID chip is a synthesizer that modulates wave functions into harmonics and subtones to make sound. SID stands for Sound Interface Device. This chip has 3 voices, which allows us to play 3 sounds simultaneously. For each voice, the SID also provides 4 different kinds of basic functions to generate sound with. In addition to the functions, the SID also provides us ADSR envelopes for adjusting the amplitude of the sound generated. Since it's also one of the few analog chips in the Commodore, the analog interface to paddles is actually present in the SID chip as well as the random number generator. And finally, it gives us 4 filters that we can use across all 3 voices to provide subtractive synthesis of sound. Each voice in the SID is composed of an oscillator coupled with a mux that allows us to select which function to use, which then outputs to an ADSR envelope generator. And finally, once all of those have completed their outputs, they're routed through the filters and finally to the speaker. Additionally, Voice 3's oscillator is available as a register to the CPU. The 4 functions that we covered earlier are the sawtooth wave, the triangle wave, which produces a very smooth sound similar to a sine wave, the square or pulse wave according to the SID documentation, and finally the noise generator. It's not really a wave, but it does produce noise. Of the 4 waves, the triangle is the only one that can be fed through the ring modulator. Additionally, the square wave is the only one whose duty cycle is adjustable. So now we know what kinds of sounds we can produce, but we need to know how we can add expression, and this is where ADSR envelopes come in. ADSR envelopes are the breadth of the sound, the expression, the dynamics of a particular sound. As such, these envelopes only control the amplitude of the sound, not the frequency, or the phase, or the pulse width, or any of those things. ADSR is an acronym that stands for attack, or the time it takes to reach a peak amplitude at the beginning of a sound. Decay, or the time to reach the sustain amplitude. Sustain, or the absolute amplitude at which a sound is held. And release, or the time it takes to reach 0 amplitude after the note is released. Sustain is held until the voice is gated off by the gate bit, and then the release waveform occurs. As an example, take this identity pulse wave that we have on the left. If we add the ADSR envelope to it, we end up with something like this. First, the attack ramps the audio up to the peak. Immediately afterward, decay brings it down to the sustain level. Sustain is held until the gate is released. And finally, the release occurs and it drops back to 0. As for filters, the SID provides 4 filters that we can use to change the sound across all 3 voices. The first one is the low-pass filter, which sounds very bassy. The next is the high-pass filter, which covers basically treble sounds, high-pitched frequencies. The third is the band stop filter, or notch filter. And the last is a band pass filter, which basically makes the audio sound very telephone-like, with no lows and no highs. All of these filters' cutoff frequencies are adjustable with a cutoff register. This allows us to tune the sound more specifically to the sound that we want, and actually makes the SID sound more like a SID rather than a generic chip. The SID has a small number of registers per voice that we have to be concerned about. The first two are voice 1's oscillator frequencies. The next two are the pulse width, or duty cycle, of the square wave. Next comes the control register, which allows us to turn on/off each voice, gate it on and off, and then also choose which wave to use in that voice. The last two registers contain the 4 nibbles that control the ADSR envelope. And after voice 1's ADSR registers, we have the same registers set up for voice 2 and then voice 3 in the same order. After the voices, we have 2 more registers to control the filter cutoff frequency, followed by the resonance and filter control register, which allows us to make some very interesting sounds. D418 allows us to adjust the overall volume of the SID and also set the filtering mode. After the filter mode, we have the paddle registers. And finally, voice 3's oscillator output and its ADSR output. Okay, so now that we've gone over all the registers and the generic behavior of the SID, let's actually write a program and make a sound with this silly thing. Shall we? Our first program will be relatively simple and focus on playing a single note. Since the program is so simple, we can also use it as a means to play with the various parameters used in voice 1. The first thing our program does is disable interrupts to prevent BASIC from messing with the SID while we're making a note. Next, we make sure that the SID is playing at full volume. After we set the output volume, we set voice 1's ADSR envelope. In this case, we choose a short time for the attack, a very short decay, a moderate sustain, and a fast release. This should produce a staccato sound. Next, we set the frequency to play a middle C note. At this point, we're ready to turn on the oscillator and set our voice to use the sawtooth wave. The minute this store instruction completes, the SID starts outputting sound, but to make sure we don't mute it too early, we use a familiar delay pattern to stall the 8502 for a few milliseconds. After the stall, we gate off voice 1. This doesn't turn it completely off, but allows the ADSR envelope to release and end in a pleasing reduction in volume, rather than cutting it off hard. Finally, we re-enable interrupts and return to the caller. Now that we've got our program, let's see what it sounds like. That was pretty easy, but what does it sound like if we use a long attack and a long decay? Notice how our program is finished, but the sound is still playing. This is because we haven't disabled voice 1's oscillator, but instead gated off the sound, and the ADSR envelope generator is still running. Alright. Okay, so at this point, we've played a generic sawtooth wave. But that sounds, well, generic. So let's see if we can make this sound a lot more unique. Let's make it sound like a SID chip. And the way we do that is we actually start using the filters, ring modulation, and start using the other voices. This next program won't be all that much more complex than the first one, so we'll use it as a tool to play with parameters again. First, let's try out ring modulation. The first part of our program does the same as the last. It sets the output volume and the ADSR envelope for the first voice. Afterward, it sets the frequency for a middle C note. At this point, we diverge from the original and set voice 1's control register to use a triangle wave instead of a sawtooth. From here, instead of delaying in an empty loop, we instead set voice 3's oscillator frequency to the incrementing values of x and y. This causes the frequency to slowly ramp up until it reaches the maximum value of FFFF. Finally, we clean up by gating off voice 1's ADSR envelope, re-enable interrupts, and return to the caller. Now that we have our program, let's hear what ring modulation actually sounds like. I'll overlay an oscilloscope representation of the sound at the same time so we can see what the SID produces. Let's hear that again. This is the result of the SID modulating the triangle wave with the frequency of voice 3. It doesn't matter if voice 3 is on or if a wave function is selected, the result is the same. Additionally, this only occurs with the triangle wave. If we select the sawtooth wave instead, we'll just get a normal sawtooth sound. Now that we've heard what ring modulation sounds like, let's play with another of the SID's weird behaviors, and try oscillator synchronization. In this case, we're re-triggering the sawtooth wave using the frequency set in voice 3. Again, like with ring modulation, it doesn't matter if the third voice is on or off, only the frequency of its oscillator matters. To round things out, let's see what re-triggering a pulse wave sounds like. In this case, the duty cycle of the square wave remains constant, but because the start of the wave is re-triggering at an increasing rate, eventually we end up with a constant amplitude and the sound seems to stop halfway through. Finally, let's see how re-triggering noise behaves. Since we're hearing white noise, re-triggering the wave causes a cycling effect in the noise. This can be used to good effect to create unique sound effects. These experiments are all fine and good for sound effects, but if we want to really hear the power of the SID, we need to construct a way to play a full song. First, we'll need a way to represent the pitch for notes in a song. Since the SID only understands frequencies, we can't tell it to just play a middle C. We have to tell it specifically which frequency to play. Each note has a specific frequency in hertz. But wait a minute, the SID only understands integers for its frequency values. To find the frequency for a given note mathematically, we can use the formula 2 raised to the t multiplied by 1/12. But to calculate the note for the SID, we have to use a different formula. Instead, we multiply the note frequency that we already know by a given constant, divided by the clock rate of the computer. Unfortunately, this requires that we A, already know the actual frequency of the note we want to play from the earlier formula, and B, have to do lots of multiplication and division to get the actual values. Instead, we can use a note lookup table, where we pre-calculate a set of frequencies to use for a given song. Additionally, we can represent the song as a series of byte values that represent offsets into the frequency table. Effectively, we end up building a double indirect lookup table, where we map the current note to a frequency in the note table and then tell the SID to use that frequency for a given note. In this case, because we're working at the 128's monitor, we'll start a scale at location 1400 and put the song at location 1500. So now that we know how to represent a song in memory, let's figure out our player program. First off, we need to initialize a few things, so we set our current note to 0 and set our voice settings in the SID. Next, we start the beginning of our player loop. The first step is to load the current note from the song table into the X register. Next, we use the X register value as an offset into the note frequency table to load the high byte of the frequency into A. Once we have the first half of the frequency value, we can then store it into voice 1's frequency register. Then, we increment X to load the next byte and store the second half. Now that voice 1's frequency is set, we can trigger the note. Then we delay so we can hear the note, increment our current note value, gate off the voice, and then finally go back to the top of the loop. Unfortunately, in this diagram, I missed our exit case at the top. We should exit the loop when the note number is 0. Now that we know what our program has to do, we can start writing it. To start, we're going to reserve a byte for tracking the current note. We use a BRK instruction here, not because it'll execute, but because it encodes to 0. Next, we have our voice setup routine, which will set the ADSR envelope for voice 1. Following that routine, we have our start routine, which sets the VIC's overall volume and then falls into the player loop. At this point, we're into the main routine of the music player. It follows essentially the same flow that we did on the whiteboard, with some minor tweaks. The first change is that we're using FF instead of 0 to end the song. We do this instead of using 0 because otherwise we'd have to offset the notes in the table by 1. The next change is that we shift the note index to the left by 1. This is because we're dealing with 2-byte values, and otherwise we would accidentally end up pointing to the wrong place as indexes increase. Other than those two changes, the flow is essentially the same. We load in the current note, we load in the frequencies from the frequency table, and then we start the voice as normal. The other half of this function is more of the same. We delay for 65,000 iterations to let the note play, we gate off the note, delay another 512 iterations to let the release occur, and finally return to the top of the loop and play the next note. The last part of our code is the exit routine. This simply turns off voice 1's oscillator and resets the current note to 0 before re-enabling interrupts and returning to the caller. Now that our program is entered, we can type in our two tables. The first one at 1500 hex is the song table, and for now, we'll just put in the notes in an ascending major scale. The last table at 1400 hex is the note to frequency table. This is an array of 7 16-bit values representing the frequencies of the notes in ascending order, starting at middle C. If we were to optimize this, we wouldn't use these values in a 2-byte array like this, and instead separate the values into 2 arrays. This would allow us to use a single index for both high and low values without needing to shift the index left by 1. These register values I pre-generated using a spreadsheet and only picked the major notes from Octave 3 for ease of entry. A link to the spreadsheet is in the description below, but do note, in a real program, I would use a pre-generated assembler file instead, with just the octaves I know my song would need. Now that everything is entered, we can test the program. Even though we entered a simple ascending scale, we can change the song to play anything in the C major scale. For instance, I can make this play Twinkle, Twinkle, Little Star. So that's about it for the basics of the SID chip. For the next episode, to get into more advanced subjects, we're actually going to cover the Buddy Assembler, specifically the eBud tool that I have currently hosted on the website. Now, I'd like to give a great shout out to my patrons. Thank you very much for being patient with me. In this particular situation, between COVID-19 lockdown and other issues that cropped up, it's been about 6 months since I've done these videos. Now, I hope to get back into our regular cadence of 2-week episodes, but it may take me a little while to get back up to speed, so please bear with me. In the meantime, thank you again so much for helping me out through Patreon, and if you'd like to help out in addition, you can go to my Patreon page in the description below. And aside from that, well, I'll see you in the next video.